What's up, guys? Uh, we are studying simple harmonic motion, and today I'll be talking about graphs of various quantities in simple harmonic motion. Okay, so graphs in simple harmonic motion. Now, there are two kinds of graphs. One is variation of a physical quantity with x, this is type 1. The other could be variation of a physical quantity with time t. Okay, so these are the two kinds of graphs can be asked. As I've already told you, if you remember, I solved for various quantities in terms of x. So velocity as a function of x, or the potential energy as a function of x, kinetic energy as a function of x, acceleration as a function of x, and then I tried to solve these expressions as a function of time t. So when I was solving as a function of time t, sinusoidal functions were derived. Okay, so let's see how the graphs will vary. So first, variation with x, variation with x. So first can be variation of velocity, acceleration, total force on the particle. Okay, and uh, potential energy, kinetic energy, and total energy. Okay, these are the quantities that can be asked how they vary with x. So the simple thing is always write the expression. If you know the expression, you can draw the graph instantly. Very easy. So how the velocity varies as a function of x, we all know, plus minus omega under root a square minus x square. This is the variation. If you are not sure how this formula has been derived, you can check my previous videos. Acceleration as a function of x is minus omega square x. Total force is nothing but mass times acceleration. So this will be minus m omega square x. Potential energy as a function of x is half k x square. What about the kinetic energy? Kinetic energy is no different. If you know the velocity, you can find the kinetic energy. Okay, kinetic energy will be half m v as a function of x square. This will be half m omega square a square minus x square, and the total energy as a function of x will be kinetic energy as a function of x plus potential energy as a function of x. You can clearly see half kx square will cancel out. M omega square is nothing but k. If you remember, omega is nothing but root k upon m, so that m omega square is k. So this will be half k a square. So total energy as a function of x is a constant. I've already told you that total energy does not change in simple harmonic motion. It is constant provided that there are no dissipative force in the system. Okay, so we have all the expressions with us. Now let us try to draw. First is the variation of velocity. So if you see this graph, what kind of uh, locus this graph is representing? If I consider, if I say that Vx is y, then y by omega whole square plus x square is nothing but a square. Okay, or I can write it further as y upon a omega whole square plus x by a whole square is nothing but 1. And we all know that x square upon a square plus y square upon b square is nothing but ellipse. So this graph is nothing but ellipse. So this is how it will vary. I made it really bad. My god, this is going to take forever. Okay, so this is nothing but ellipse, and considering that omega is greater than 1, so a omega will be larger quantity than a, so the graph will be something like this. Now this is good. This is the velocity and this is the position x. This point is nothing but a, and this point will be a omega. Okay, so you can clearly see, suppose the this is the spring block system. So when the spring block system is at maximum extension, let us say here it is extended by a, at that instant the velocity will be 0, so it is here, particle is here. As it start moving towards the left, so velocity will be negative because velocity is in the negative direction. So the particle starts moving the like this. This is the variation of velocity, not the particle, but I'm just showing you how the velocity, in which direction velocity will go. Okay, so this is how velocity starts to change. When the particle is at the mean position, velocity will be maximum and its value will be minus omega a in the negative direction. Okay, and then again when it is at minus a, the velocity is again 0. It is at the maximum compression and then starts to move towards omega a. Okay, so this is the variation of velocity with x. Next is acceleration. So acceleration as a function of x is minus omega square x. This is nothing but a straight line whose slope is negative. Omega square is a positive number and minus omega square is a negative number. So a straight line with negative slope which passes through the origin, because at x is equal to 0, acceleration will be 0. So this will be a straight line like this. Okay, very simple. And this is the x coordinate, this is a, this is minus a. So when the block has been extended and is at plus a, and that condition the acceleration is maximum and the value will be minus omega square a, and it will be pulling towards the mean position. So acceleration is negative and in the maximum possible value, so minus omega square a. As it begins to move towards the origin, the acceleration is still negative, it is still pulling it in the towards the mean position, but the magnitude is coming down. At the origin, the spring is in its relaxed position, so the net force is 0 and hence the acceleration is also 0. Then it begins to, as it start moving towards negative x-axis, now the force of the spring will be in the positive direction, and so the acceleration will be in the positive direction. Okay, so now the acceleration, as it goes in this region, the acceleration is positive. Okay, and finally at minus a, the acceleration will be maximum and the value will be plus